This is going to be a topic recap video covering AS and A-level trigonometry. Okay, we're going to start off with the AS part of trigonometry. And we'll start with the trig ratios and area. So we start with the trigonomic ratios, which are based on right angled triangles. And then we move on to the trigonometry for non-right angled triangles. So you'll recognize these as the sine rule and the cosine rule. Now with the sine rule here, it comes in two forms. One is the reciprocal of the other. If you're trying to find a side, use this form here where the side is at the top. If you're trying to find an angle, use this bottom form here where the angle is at the top. Now with the sine rule, you get something called the ambiguous case where the angle could actually be acute or obtuse. So if you've got the acute angle, all we do is 180 minus that acute angle to find the obtuse angle. Or if we have the obtuse angle, again we just do 180 minus the obtuse angle, and that will give us the acute angle. And then we finish off the ratios and area with the area of a triangle giving us half AB sine C, and the AB and C relate to this triangle here. Next we're going to look at identities, and there's only two of them, and that is tan theta is equal to sine theta over cos theta, and the other identity is that sine squared theta plus cos squared theta is equal to 1. Now this is actually the equivalent sign, and it basically means that this is true for all values of x, and this identity here is known as the Pythagorean identity because it's based on Pythagoras. Next we're going to look at how we can work out some exact values for sine, cos and tan, and these exact values are just based on these two triangles here: an isosceles triangle with sides 1, 1 and root 2, and a triangle here with angles of 30 and 60 and sides of 1, root 3 and 2. So from the first triangle, we'll get sine 45 is actually equal to cos 45, which is equal to 1 over root 2. And if we rationalise the denominator, that's root 2 over 2. Sine 60 is equal to cos 30, which is root 3 over 2. Tan 30 is 1 over root 3. Rationalising the denominator, you get root 3 over 3, and tan 60 is root 3. Next up are the graphs of sine, cos and tan. So here we go, sine, cos and tan. These graphs carry on forever in both directions. I've just done parts of them. The graphs are periodic, which means that they repeat every 360 degrees, and something important happens every 90 degrees. The graph either crosses the axis, it has a peak, it has a trough, or in the case of tan, it has asymptotes, and these asymptotes occur every 180 degrees in both directions, with the first one here being at 90 and the first negative one being at negative 90. And asymptotes are just these gaps in the graph where the graph doesn't cross the axis. So this part of the graph is going to shoot off to positive infinity, it's going to keep going up. This part of the graph is going to shoot off down to negative infinity with a undefined value here. So if you tried working out the tan of negative 90 or 90 or 270 or so on, your calculator is going to come up error. Now from these graphs we can get some other identities, which is the sine of 90 plus or minus theta is equal to cos theta, the cos of 90 minus theta is equal to sine theta, and the cosine of 90 plus theta is equal to negative sine theta. And linked to graphs is this thing called a cast diagram, which is going to be useful for the next bit, which is solving equations. And a cast diagram basically summarizes everything that's in a graph, which is shown in a linear fashion straight across round a circle. So cast, C-A-S-T, that's where the name comes from. Each letter is the beginning of a word, and it's basically telling you in which part of the cast diagram a graph is positive. So I can see that between 0 and 90 degrees, all the graphs are positive, they're all above the axis. Then between 90 degrees and 180 degrees, only the sine graph is positive, and so on. I've got a whole video on the cast diagram, so I'm not going to go through the whole thing here, but it's summarizing all three of these graphs in a single diagram, which means when we come to solve trig equations, rather than have to draw the graph out, we can simply use the cast diagram. So last AS trigonometry topic is solving equations. So the steps are: you find the first solution or the principal solution on your calculator, you find the other solutions on a cast diagram or graph if you prefer, then you solve the equation. So I'm going to give an example. Okay, so let's say we want to solve this equation. Cos 2x minus 20 is equal to 0.3 in the range between 0 and 360 degrees. So the first step is to adjust this range to fit what we have here. So I'll take all three sides of this inequality, multiply it by 2 and subtract 20, and I get a new range between 0 and 700 degrees. So that means that when I use the cast diagram, I'm going to go from 0 to 700 degrees, or if I'm using a graph, again from 0 to 700 degrees. Next, I do the cos inverse of both sides of this equation, and this will give me the first or principal solution. So that will give me 2x minus 20 is equal to 72.4 degrees rounded to 2 decimal places. What I don't do at this step is try and solve this and find the other solutions. I find the other solutions first, then solve this equation. So I know that on my cast diagram I need to go from 0 round to 700 degrees. So I'm just going to highlight that so you can see where we need to go. So we're starting here, we go round. So we've now got to 360 degrees. That means we carry on going around again on our cast diagram, and we stop 20 degrees short of going around a second time because that would be 720 degrees. So I'm looking for solutions in this range. So I mark on the principal solution that I found, and that is the 72.54 degrees. So I'll just mark that on here like this and mark this as 72.54 degrees. Now, when using a cast diagram to find other solutions, if we're solving an equation for sine, what we do is the line that we've drawn, that principal solution, we reflect in the y-axis. If we're solving for cos, we reflect that line, principal solution, in the x-axis. And if we're solving for tan, what we do is we would just make that a straight line. So I've reflected that line in the x-axis. So this gap here is also 72.54 degrees, and all I need to do is to read these values off. So going around, we've already got the first one, 72.54. Going around to here, this is equal to 360 minus 72.54 when we go around the first time, and that will give me 287.46, again rounded to 2 decimal places. Then we keep going, and as we go around, the next solution, as we go around the second time, will be 360 plus 72.54. and that's 432.54, and then as we keep going, this one here is going to be 720 minus 72.54, and that gives 647.46. Now what we do is we take all of these values, we add 20 to each one, and then we divide by 2 to find the final solutions. And those solutions are 46.27, 153.73, 229.23, and 330.77. So that completes the AS trigonometry recap. So now we go through the A-level trigonometry. So we start with the identities. So we start with the reciprocal identity. Sec theta is defined as 1 over cos theta. That also means that cos theta is 1 over sec theta if you reciprocal both sides. Cosec theta 1 over sine theta. So sine theta is also 1 over cosec theta. Cot theta is defined as 1 over tan theta. So tan theta is also 1 over cot theta. So I'm going to put my equivalents in because this is true for all values of theta. Now, if we start with the Pythagorean identity that we had from AS, if we divide everything through by sine squared, we'll get 1 plus cot squared is equivalent to cosec squared, or if we divide everything through by cos squared, we get 1 plus tan squared is equivalent to sec squared. And we also have that cot theta is going to be cos theta over sine theta. So compare that with tan theta, which would be sine theta over cos theta. Next, we move on to the addition formula. For sine A plus or minus B. So you've got sine A cos B plus minus cos A sine B. Cos A plus or minus B, cos A cos B. Now notice the signs the other way around. So when we have a plus over here, we have a minus over here, a minus here. This becomes a plus. And then tan A plus or minus B is equivalent to tan A plus or minus tan A tan B. At the bottom, 1, again the signs flipped over. minus plus tan A times by tan B. So when this is a plus, this is a minus. When this is a minus, this is a plus. Now, if we take this addition formula and basically do A plus A instead of A plus B and A plus A and A plus A, we get what's called the double angle formulas. So replacing the B with an A and using a plus sign, sine 2A will become 2 sine A cos A. Tan 2A will become 2 tan A, so you've got tan A plus tan A, over 1 minus, because we're using the plus here, minus tan squared A. Now remember, that tan squared A could be replaced with sec squared minus 1 if you needed to. And cos 2A comes in three forms. Cos squared A, because you'd have cos A times cos A, minus sine A times by sine A, so that's sine squared A. And if we use the identity sine squared plus cos squared is 1 and make substitutions, we can write cos 2A also as 2 cos squared A minus 1 and 1 minus 2 sine squared A. Now this particular formula identity is going to be very useful when you come to do integration, and if you want to integrate sine squared or cos squared, we can rearrange this identity to get cos 2a and integrate that instead. Next up is radians, and this is just a different way of measuring angles. So here 360 degrees of full turn is 2 pi radians, a little c here just indicating that we're using radians. So if we half both sides of that, we get 180 degrees is pi radians, 90 degrees is pi over 2, and we can get other angles as well. So for example, 45 degrees is going to be pi over 4, 60 degrees will be pi over 3 if you divide these by 3, and so on, 30 degrees pi over 6. So it's useful to remember things like that. 1 degree is equal to pi over 180, and 1 radian is equal to 180 over pi. Now when an angle is measured in radians, it makes it very easy to find an arc length or the area of a sector. Arc length is just the radius times by the angle subtended at the center in radians. The area of a sector is half r squared theta. Again, this angle is the angle subtended at the center, basically the angle in radians. Next, we're going to be looking at the graphs of these new reciprocal functions, and also the graphs of the inverse functions. Right, so we have the graphs of cosec, sec, and cot. Notice that all of the graphs have asymptotes. The graphs of cosec and sec don't go anywhere between 1 and minus 1. There's no part of the graph there. And the graph for cot looks a bit like the graph for tan, but it looks like it's sort of turned around the other way. So you do need to know these graphs. They carry on forever in both directions, and I have marked on a few angles here, and you could have these angles in radians as well, just like you could have the angles, important angles on the graph for sine, cos and tan given in radians as well. And then here we have the inverse graphs. You can think of this like tan inverse, sine inverse, and cos inverse, and arctan. Its asymptotes are now horizontal. They were in the original graph vertical. Everything on the x and the y gets swapped over. Arcsine, it's like a chopped off version of the reflected graph of sine in the line y equals x. So it has a limited range and domain, and the same with arccos, a limited range and domain. Arctan doesn't have a limited domain. It goes on forever in the x direction, but it does have a limited range. It's going to always be less than pi over 2 and greater than negative pi over 2. Lastly, we're going to look at how we deal with some trigonometry written in this form: a sine theta plus or minus b cos theta. We're going to change it to a different form because trying to sketch this graph is going to be tricky. Trying to solve an equation that has this in, or an identity that has this in, can be tricky, but we can write it in a much more straightforward form. So we'd write it in the form r sine theta plus or minus alpha, where r is just a square root of a squared plus b squared, so we do Pythagoras on those two numbers, and alpha will be the tan inverse of this number here, b over a, and you can match this up with the expansion for sine a plus or minus b. So have a look at this, compare it with this, and then you can see how we get the values of r and alpha. And the very last thing, if we have something written in this form, a cos theta plus or minus b sine theta, we can write it in the form r cos theta, and notice the minus plus alpha, so the sign here will be the opposite of this one here. We find r in the same way as we do here, square root of a squared plus b squared, and we find alpha in the same way as we do here. This will be the tan inverse of b over a. And with this, compare it with the expansion for cos, and that will help you understand where we get the r from and where we get the alpha from.